Okay, in this video we're going to be talking about Bohr's model, and the first question we come to, can light come from an electron? And so that's a very odd question to ask. And if we look at the image to the right, we see a diagram of Bohr's model. And so in the middle you have the nucleus, and you see the various energy levels starting with 1, 2, and 3. Now, the electron that you see here is in the first energy level. Now, what will happen here is that if we input some energy, what will happen is that electron gets excited, all right, and it gets excited into one of the upper levels. Now, you know that if you punch someone and they're not knowing it, they're gonna get irritated and they're going to get excited. And so one of the things that happens is that the energy that gets built up during this excitement has to go somewhere. So when that electron travels back down through and it releases this energy, it releases this energy in the form of light. And that's what you're looking at here, is you're seeing light come out as a product. And so depending on how much energy changes in this case will really determine the wavelength and the color of light that you see. And so Niels Bohr proposed this model to describe how electrons move throughout orbitals, and this movement throughout the orbitals is what results in the releasing of light. Also recall that he introduced the idea that electrons are in discrete energy levels, and that's where you have n equals 1, n equals 2, and this can go all the way up to n equals 7 theoretically. So as we talk about the electron and how it transitions, and we try to understand what types of light that gets emitted during that transition, we can look at the hydrogen atom and we can learn a lot from that atom. So this is an alternate PowerPoint, and this just kind of gives you an illustration of the hydrogen spectrum. And so hydrogen gas is a gas that emits specific colors, and you can see here that it emits sort of a purplish bluish colored gas. And so we can't see the individual colors that show up, but using a certain tool, a diffraction grating, we can actually separate the spectrum of light that shows up. And so you see the gas tube behind it, and you see the viewer scope here. So what happens is the light passes in this direction, and there's a filament right here that will break up that light, and you'll see the different color spectrums show up on the back right hand side of this instrument. And so the colors that you see show up are, in this, you'll see red, a teal color, and a dark blue color. And so this is the spectrum that you see. And so this is a spectrum that's specific for hydrogen gas. And so when we talk about Bohr's model, and Bohr's model is only good for the hydrogen atom. If we go beyond that, it starts to have problems, and that deals with Schrödinger's equation, which we'll get to in a future video. So when we talk about the different spectrums that we can see, we have to talk about two different states: the ground state versus the excited state. I kind of talked about that in the previous slide, where the ground state's the lowest energy state for an atom, and then when it gets impacted with some form of energy, it gets excited, and then the state in which the atom has higher energy level. And once that excitement releases the energy, you get a color spectrum. And so what we see here on the left are the different spectrums of what we, some of different elements. And so the first one we see at top here is the sun. And the sun, if you take a prism and you hold it in front of the sunlight, you'll see the rainbow show up. And then we call that a continuous spectrum. That's just white light that illustrates. So this would be what you would see during a white light demonstration. So you get all the colors in the rainbow, Roy G. Biv. Now, hydrogen gas is different because hydrogen gas is only giving you specific lines, and so we call that a line spectrum. And so here in the second one, we see the hydrogen gas spectrum. Now below, we see helium. All right, helium is not something we come across, but the third one, which actually was the fourth one, this is mercury. If you take a fluorescent light and you cut it on, and you use a special film that holds in front of your eyes, what you will see is these individual colors show up. And these are the main colors that you see in a fluorescent light bulb. And so we call that a line spectrum. A line spectrum is just specific lines that show up within a spectrum. And then the sun shows a continuous spectrum. So this is an example of the Bohr model, and it illustrates the different wavelengths that you get from the transitions that can be observed. So let's say that we started from n equals 4 and we went back down to n equals 2. So we find 4. All right, so here's 4, so track that around. All right, so 4 is going to go to 2, so we're not going to look at that line. All right, here we are. So 4 drops down to 2. And so what type of light would we expect to see here? All right, comes straight down. So at that type of light, we would see 486 nanometers. And that's roughly blue light. So we would observe a blue color. And so that's how we use this diagram here. This diagram is you figure out what energy level you're on, and then what energy level you're traveled down towards. So let's say we had from n equals 6 to n equals 1. So we find 6, come around, and here's the first one. This goes down to 1. And what energy do we get from this transitional change? We get 410 nanometers for that transition. Actually, I lied. I chose the wrong one. So let's come around. What do we have from 6 to 1? I don't think we have 6 to 1. But you know what? We can calculate it. We can use Rydberg's equation. And Rydberg's equation is given to you right here. Rydberg's equation is equal to minus RH. Now this is solving for energy, so there's going to be a few other problems that we have to work through before we get to our wavelength. But we have to know RH. RH is Rydberg's constant, which is 2.18 times 10 to the negative 18 joules. Now NF is the final energy level, and NI is the initial energy level. So if we were going from n equals 6 to n equals 1, we could plug this in and we can solve for it. So the final was 1 and the initial was 6. So we can plug these values in here. And that's what we're going to do right now, is we're going to plug these in. We're going to solve for the energy of that transitional change. All right, so to do this, we're going to take negative 2.18 times 10 to the negative 18 multiplied by 1 divided by, all right, the NF was 1 squared. 1 divided by 1 is 1, minus 1 divided by 6 squared, which is 36. And we get negative 2.1 times 10 to the minus 18 joules. Now, the negative sign just means that energy is released. This is an exothermic process. To figure out the wavelength, what we're going to have to do next is we're going to use Planck's equation. E is equal to h nu. And we're going to solve for the frequency by dividing the energy by Planck's constant. So I'm going to go ahead and do that now. Remember, Planck's constant is 6.626 times 10 to the negative 34. So I'm going to take the energy and I'm going to divide that by 6.626. 34. Do not worry about the negative sign. All right, the negative sign just tells you that it's exothermic. We don't need to worry about keeping that negative sign here. So I get 3.20 times 10 to the negative, or times 10 to the 15th. Not negative, but 10 to the 15th. And it's a reciprocal seconds. So the next step we're going to take here is we are going to calculate the wavelength using the speed of light equation. And so we know the frequency here. We're going to take 3 times 10 to the 8th. We're going to divide it by 3.2 times 10 to the 15th. And that will give us an answer in our wavelength. So that gives me 9.37 times 10 to the negative 8 meters. So what I'm going to do now is I'm going to take my 9.37 times 10 to the minus 8 meters, and I'm going to convert this into nanometers. So we're going to multiply by 1 times 10 to the 9th. So doing that now, we get 93.8 nanometers. So that is the wavelength of light that would be released from 6 to 1, and that is a pretty low wavelength, pretty small wavelength to begin with, and this would be representing UV light. And so if we don't have that chart, you can use Rydberg's equation to solve for that change. Now, the problem that you see in front of us, all right, we can utilize this information of Rydberg's constant and this equation to predict what the answers to the following questions. So I'm going to erase what's on the slide here, and we'll work out this one here first. Okay, so which transition is of the highest energy? Well, I like to draw a little diagram here. There's 4s for the highest, and this is a diagram we all can draw. This is 1, 2, 3, and 4. So we have 4 to 1. That's the first transition. 4 to 3. 4 to 2. And then 3 to 2. So looking at the way I've drawn this out, which one looks like it's going to have the biggest amount of energy released? Well, 4 to 1. You can definitely see that there's a larger space in between that compared to the others. So transition 1 would transition 1 would be the answer to part A. Now looking at part B, it says which transition of the lowest energy, still using this chart. Well, we can see that 4 to 3 has the smallest gap. So 4 to 3 would be the answer there. So number 2 would fill in there. And then the last question says, which transition is of the shortest wavelength? Well, highest energy yields shortest wavelength. That's a relationship that we talked about already. It's an important relationship. So always remember the higher the energy, shorter wavelengths. Shorter wavelengths always will have the most energy. Gamma rays has the shortest wavelength, so they're going to have the most energy, and that's why we don't want to get impacted. But to answer this question here, which transition is of the shortest wavelength? Well, the first transition answers that question. So